This is the Bad Wolf traffic simulator for ENG6 Winter 2012. My name is Louis Edelman.
I'm Harsiv Singh.
I'm Fatima Prada.
We're going to start out by showing you some features of our GUI interface. Just to give you a brief intro into how the program works, then we're going to delve more into the code and some of the logic behind the simulation. So as you can see, the GUI works to scale, but it does work best when it is full screened. We've got some basic GUI features. We've got our buttons down here in the left corner, in axes to output our moving cars onto the road. These lines are plotted just using a standard plot function and the hold command. Since our cars are rendered using the rectangle function, the road doesn't have to be replotted through each cycle. Down here in the bottom right, you'll see we have areas where data for instantaneous fuel usage by all 20 cars and instantaneous CO2 emissions by all 20 cars will be output. Top right corner of the axes, we have a small frames per second indicator just to give users an idea of how fast the program is working. So we'll start by showing you a run through. The cars have a staggered start at random velocities off. When they reach 100 or the end of the road, they will go to a random distance back off screen, which effectively gives them a random restart time.
The rectangles are being plotted using the rectangle command as said earlier, and we're using a for loop to plot all 20 rectangles. In the rectangle command itself, we have a position where we say where the original object is located and where to create the rectangle. Then we give that rectangle a specific curvature. In this case, the curvature is 0.6 on the x side and 0.59 on the y. And then finally, we give each car, based on the type of car it is, we give it either a cyan or a green. This is run through 20 times to create 20 rectangles.
Some other features of the GUI. Start and stop will pause the simulation and resume it at the same point. You can pause the simulation and reset it to the beginning, and it will start over. Same staggered start, same random velocity selection that would have happened when the GUI initially opened. As you can see, as a side effect of this iterative method, even though the data is reset, the program has slowed down from its beginning. Final feature of the GUI is our data plotting system. You see here, after you pause the function, you can plot the data you've done so far, see how your fuel usage is changing, and your carbon emissions are changing over the time of your simulation, which is something I believe that is unique to our simulator. Let's get it started again. As you can see, vehicles are changing lanes at random times. They are going to be teleporting between lanes. We felt that it's still distinct enough to show that the vehicles are changing lanes, but doesn't incur a lot of the complexities and issues, especially when it comes to calculations that happen with a smooth lane change. We determine if a lane change is safe by referencing the lane the vehicle's in, and then finding the location of all vehicles in the adjacent lane. And if there are no vehicles in that adjacent lane within a certain range, let's say 7 units behind, 7 units forward, for example, then the vehicle will change lanes and maintain its forward velocity. This will also refresh within the object system which lane it's in, allowing the rectangle command to properly plot it in the next iteration.
To get the carbon emissions, you would multiply the carbon dioxide emissions of each individual car depending on the random simulation that's given in the GUI times the conversion factors in order to get pounds per hour at the end times the velocity. In order to get the fuel consumption, you would do the velocity randomly given by each car minus the velocity times the fuel economy decrease that's given in the data as well, divided by the combined fuel economy given in data as well to get gallons per hour.
To prevent collisions within lanes, we've used 2 for loops to compare all the possible cars, and then by limiting it down to comparing only cars in the same lane, we can apply some velocity modification to one specific car to prevent their collision.
The collision avoidance function has been repeated in 2 spots before the lane change and after the lane change, just to double check so there is no collision. Or if the collision is about to occur, it'll slow down the car that's in the behind by a factor of 0.3 in the velocity, and speed up the car that's ahead of it by a factor of 0.1 miles per hour for the car in front of it. Also in the slowing down or collision avoidance system that we have written, if any car in the GUI is currently running below 55 miles per hour, the system will automatically upgrade its speed to 55 miles per hour to avoid massive traffic jams in our GUI.
Our last point about the functioning of this system is while the system is continuously tracking 20 cars, because the system has to stagger the cars apart and there is a random re-entry time, the chance that all 20 cars will be visible on the screen is fairly slim, and again, because of the randomness, the density of the vehicles is going to fluctuate. Even though a car is off screen, it is still moving and still factored into the calculations, which was a stipulation of the project statement. The vehicles seen in the GUI are obviously not to scale. If they were to scale, they'd be points, and we wouldn't get the effect of a vehicle moving along the highway. The visual is less important than getting the point across, which is why we made this decision.